Hi everyone. So today we're going to be talking about how derivatives affect the shape of a graph. So a lot of what we're talking about today is going to be review. It's going to be stuff that we talked about actually earlier in the quarter when we were first learning about derivatives. But then we're also going to learn some new stuff, basically talking about how the second derivative affects the shape of a graph of a function. And so this is a topic that we're going to spend a few days on. So today's going to be just kind of laying down the basic definitions and facts that we're going to be using. And then tomorrow's video, we're going to do a lot more examples of actually kind of working with a function and seeing how we can use the derivatives to actually figure out what the graph looks like. And then we'll continue talking about it again in the next video as well. So I want to start by, like I said, kind of reviewing some stuff from earlier in the quarter, which is talking about what does the first derivative, so f prime of x, tell you about the graph, so like the shape of the graph of a function f of x. So basically what we've seen is that if the derivative is bigger than 0, is positive, then that tells us that our original function is increasing. It's going up, because if you think about it, if the tangent lines are have a positive slope, that just means that the shape of the graph has to be going up from left to right. And then we've seen that if f prime of x is negative, then your original function f of x is decreasing. It's going down from left to right. And typically when we've written down this list, we've also talked about what happens when f prime of x equals 0. And I'm going to actually leave that off because we'll come back to that idea tomorrow. We know basically that if the derivative equals 0, then it's neither increasing or decreasing. And what we saw in last week's videos is that that means that we have something called a critical number, and it could be a local max or min, but it's not guaranteed to be a local max or min. So again, we'll come back to those ideas tomorrow and see how that fits in with everything else. So I wanted to start by just looking at an example and just looking at a graph basically and seeing how we can kind of go back and forth between information about a function and its derivative. I think that's kind of really the main idea of today's video and other videos this week as well, is being able to, whether you're given an original function and you have to then figure out what's going on with its derivative, or if you're given the derivative to figure out what's going on with the function, just being able to really kind of go back and forth and understand what you're looking at in all these different situations. So this example is the function f of x is equal to x cubed minus 3x. So I just basically want to look at this graph and talk about where is it increasing, where is it decreasing, and use that to kind of tell us where the derivative is going to be positive and where it's going to be negative. So going from left to right, we can see that this function starts by increasing. And so I want to write that down, and then we're also going to kind of write down what that tells us about the derivative. So first thing I want to write down is that f of x is increasing. And in this section, we're typically going to be talking about intervals. We're going to be using interval notation to describe the parts of the graph that are increasing or decreasing. So if we look at this, this function and assume that it continues in this direction, where it's pointing in either direction. So that means that this function is increasing from negative infinity. So with interval notation, you always put a parenthesis when you're dealing with infinity or negative infinity. And then it's increasing all the way up until x is equal to -1, right? If we're looking at the part of the graph where the function's increasing, it stops increasing at -1. And so we'd say it's increasing on the interval from negative infinity to -1. And the reason I'm putting a parenthesis at -1 is because at x is equal to -1, the derivative would actually equal 0, right? Because you'd have a horizontal tangent line. So we're always kind of leaving our intervals open with parentheses rather than brackets in this section. So if f of x is increasing on this interval, what does that tell us? That tells us that the first derivative is positive. And maybe let me just write it like this. F prime of x is greater than 0 on the interval from -infinity to -1. And then similarly, we have the graph also increasing starting from x is equal to 1 to an x is equal to infinity, right? Like basically from 1 on, the graph is also increasing. So we can also say, and I'll put it down here so that things can be in order. So f of x is increasing on the interval from 1 to infinity. Again, we put parentheses, and so that tells us that the first derivative, f prime of x, is positive on the interval from 1 to infinity. And maybe you've picked up on this already, but we always, when we're talking about intervals where things are increasing or decreasing or positive or negative, we're always giving the x values. And the way that you can kind of think about that is maybe imagine that this graph was a graph of temperature as time went on. And if someone asked you, when is the temperature increasing, you wouldn't say it's increasing from 10 degrees to 20 degrees. You'd say it's increasing from 3 to 5 p.m. or something like that. And so really when we're talking about increasing and decreasing, the kind of reference that you give is always x values, because the y values are more telling you kind of like what the outputs are, whereas the x values are telling you kind of where or when something is happening. All right, just to throw this one in here too, we also have that the function is decreasing, right? Between -1 and 1, f of x is decreasing. So f of x is decreasing on the interval from -1 to 1. Again, putting parentheses because it's neither increasing nor decreasing when x equals -1 and 1. So this tells us that the first derivative is negative on the interval from -1 to 1. So I just want to do a quick little side-by-side with the derivative. So you can say, like, I guess one point I just want to really emphasize here is that we can say this fact here, right, and this fact here, and all these facts about the derivative without ever looking at the graph of the derivative. We can make those statements just based on how f of x is behaving. We know that f of x is increasing and decreasing, and that tells us that the first derivative is positive and negative. So the derivative of our function is a parabola, right, because the original function was x cubed minus 3x, so the derivative is 3x squared minus 3. So what I just want to point out here is that is basically how the information we wrote down about the derivative, how that actually shows up here, right? So we said that the original function is increasing from -infinity to 1, and so that the derivative should be positive. And so we can see that the derivative here is positive, right? It's above the x-axis. So again, when we're talking about positive versus negative, it's really important that you don't mix that up with increasing and decreasing. So when we say positive or negative, we literally just mean above the x-axis or below the x-axis. So when the derivative is positive, meaning the derivative lies above the x-axis, that corresponds to the original function increasing. And then we can see that at the part of the function, so here we saw that our original function was decreasing from -1 to 1. We can see that that's exactly the part of the graph where the derivative is negative, right? It's below the x-axis. We're not thinking about whether the derivative is going up or down. We're just thinking about whether it's positive or negative. And then, again, we see that the derivative is above the x-axis. It's positive from 1 on, and that matches up with where this function's increasing again. Okay, so that's kind of review. Again, we've talked about that in the past, but I wanted to just review that because it's going to be a little bit different than how the second derivative affects the graph, and I just wanted to make sure that that you remembered all that stuff before we move on to something else. So actually realize I think I want another page in here. Let me just do that. Okay. So I want to start talking about how the second derivative affects the graph. So we're going to kind of do some like warming up and thinking about it, and then we'll eventually write down some, nice concrete facts. So general question is basically, what does the second derivative, so what does f double prime of x tell you about the graph of f of x? So eventually we'll have some nice like vocabulary and concrete stuff, like I said, but I want to think about this more kind of generally first. So I would think first about, what's the relationship between the second derivative and the first derivative? The second derivative is the rate of change of the first derivative, right? So I'm going to write something down here, which is that one way that we can think about the first derivative is that it tells us about the steepness of a function, right? Like when the first derivative is a bigger number, that means the graph is steeper. It also tells us whether the graph is increasing or decreasing, but at least one of the things it tells us is about steepness. So f prime of x, the first derivative, tells us about the steepness of your original graph. So if the second derivative is the rate of change of the first derivative, that means that f double prime of x is going to tell us about the change in steepness. Oops, I do that sometimes. I like link two words together. About space, the change in steepness. Does that make sense? So it's basically that, the second derivative is the derivative of the first derivative. So if the first derivative tells us about, how steep is a graph, if we're kind of keeping track of how that's changing, that's going to be the second derivative. So I want to sketch a couple of examples of functions and basically kind of use them as examples to see how the second derivative is different in these two different cases. So this is going to be one example, and then this is going to be another example. So both of these graphs are increasing, right? They're both going up from left to right. But what's different about them? I mean, just kind of, I think maybe actually a good way to think about the difference is, imagine that these graphs were representing like the position of, a person or who's running or walking or something like that. In the first one, it looks like that person would be speeding up, right? Because as time passes, they're covering more ground. They're going more quickly. Whereas the second one looks like that person would be slowing down, because as time passes, the graph is becoming less steep. So that's kind of, I think, a good way to think about the differences in these kinds of shapes. And basically what's going on here is that let's think about the slopes of the tangent lines in both of these. So if you were to take some different slopes of tangent lines on the green graph, so like maybe here and here and here, notice that those tangent lines are getting steeper and steeper. So what does that tell us? So let me write that down. So the tangent lines are getting steeper. And what does that mean about the first derivative? That tells us that the first derivative is increasing, right? Like if you were to, you could even assign numbers to these slopes. You could just estimate. So maybe the first slope is like a half, the second slope is like 1, third slope is 2. They're getting bigger. So the first derivative is increasing. So if the first derivative is increasing, what does that tell us about the second derivative? So remember, the second derivative is the derivative of the first derivative. So we can even go back to what we have here. So we know that when your original function is increasing, its derivative is positive. So if we're saying, and I can even add it in here. So if we're saying that the first derivative is increasing, the derivative of the first derivative is the second derivative, right? So if the first derivative is increasing, that tells us that the second derivative is positive. So this means that f double prime of x is positive because the rate of change of the first derivative is positive. So on the other hand, on this one, if we were to take some different tangent lines, we start off with these bigger slopes, then it becomes less of a steep slope, it becomes less of a steep slope. So in this case, the tangent lines are getting less steep. So what does that tell us? That tells us that f prime of x is decreasing. And what does that tell us? That tells us that the second derivative is negative. So basically, if your first derivative is increasing, then the second derivative is positive. If your first derivative is decreasing, then your second derivative is negative. And so there's a word for these two different shapes, and I'll define it more concretely in a moment, but this first graph here is what's called concave up. So it's kind of like it opens upward, is the way that I like to think about it. It's like if you were pouring water on this thing, water would start to kind of collect in it, right? Because it has this, like, it cups upward. Whereas this graph is what's called concave down. So if you were to pour water onto this, it would all kind of go off the sides, right? None of it would actually be caught in this because it's like you have a cup that you've flipped upside down, concave down. So the technical definition of concavity is that, so f of x is called concave down, or actually let me start with concave up, at a point. So we'll see that in when we look at some later examples, these are both examples of graphs that are like, they're both, the first one is always concave up, the second one is always concave down. But later we'll look at, we'll go back to our same first example, and this one switches concavity, right? So we'll talk more about this in a minute, but in this case, part of the graph is concave down and part of it's concave up. So our definition is going to use that fact by saying it's called concave up at a point, because the graph isn't necessarily always going to be concave up or concave down. It's really about looking point by point at what's happening. So a function is called concave up at a point if the tangent line, or actually let me say it this way, if the graph of f of x lies above the tangent line at that point. So basically, if you have a graph that is concave up, that will mean, let's actually just look at this example here. If you draw a tangent line, the graph is kind of curling up away from the tangent line, right? I didn't draw this perfectly because my lines aren't really quite lines, but you can at least see that, like, and maybe exaggerate it in your mind, the tangent line is going to be below the graph, and the graph is going to be kind of curling up away from the tangent line. And so similarly, a function is called concave down at a point if the graph of f of x lies below the tangent line at that point. So we can see that in our example on the right up here. So if we look at where our tangent lines are, the graph is kind of peeling away from them below, right? It always is lying below the tangent line. So personally, this is not really the definition that I use. I just wanted to share it because it's kind of the technical, like official definition. But again, I just like to think about, does it look like it's kind of, does it look like it would collect water if water would fall in it? And that would mean it's concave up. Does it look like the water would run off of it? That means it's concave down. So I just want to show you a few more examples of just like what they could look like being concave up and concave down, because both the examples I drew earlier were increasing, and I'm actually going to redraw those two examples. But just so that you can see a couple other ways that concave up and concave down can look. So we had this example of a graph that was concave up, and we had an example that looked more like this of a graph that is concave down. So we could also have a graph, so these are both increasing, right? Those are both going up from left to right, regardless of their concavity. You could also have a graph that is decreasing, that is concave up, and that's going to look like this. So that's an example of a graph that is concave up, but it's also going down from left to right. And then this example here would be, or sorry, that I'm about to draw, is going to be an example that is going down, so decreasing, and it's also concave down. So we can kind of summarize these by saying basically both of the graphs in this column here, these are both concave down, or sorry, concave up. And these ones here are both concave down. And then if you go, instead of going down, if you read across, these two functions are both increasing, right? If you look at the top row, both of those functions are increasing. And if you look at the bottom row, both of these functions are decreasing. So it doesn't, increasing and decreasing are like totally separate from concave up and concave down. It's really more about the shape of the graph when you're talking about concavity. Okay, so I want to go back and to the first page we had and just kind of write down what we can now say about concavity using the second derivative. So here we said, what does f prime of x tell you about the graph of f of x? So now we can say, what does f double prime of x tell you about the graph of f of x? So what does it tell you? Basically, it says that if the second derivative is positive, then your original function is concave up. And if you're having trouble remembering that fact, I would just think back to like that first example we did and just think about the fact that the slopes are getting steeper and steeper, they're increasing. And so because the slopes are increasing, the second derivative is positive. Whereas if the slopes are decreasing, then that tells you that the graph is concave down. And so that means the second derivative is negative. So there's going to be something analogous to a critical number for concavity, but I'm going to save that for tomorrow just so that we can focus more on these ideas for today. One quick thing I just want to mention, so if you are thinking about this idea of, is the graph getting steeper or not, it does matter whether the graph is increasing or decreasing. So like, for example, if we look at this graph here, in this case, the slopes are negative, right? If you were to draw a tangent line here, tangent line here, tangent line here, they're all actually getting less steep, but they're still increasing because, for example, maybe the slope of this first one would be -2, and the slope of this one would be -1, and this one would be like, I don't know, -1/4. So even though those numbers are getting you might think of those numbers as getting smaller. They're actually getting bigger, right? Because negative numbers, -2 is a smaller number than -1. And -1 is a smaller number than -1/4. So in both of these graphs in green, it is true that the slopes are increasing. It's just that when they're negative, it's kind of a little funny. It's not what you would think of as increasing, but technically the numbers -2, -1, -1/4, those are increasing. But I think if you're trying to kind of have a good visual that helps you remember how concavity relates to derivatives, I think maybe thinking of this picture in your mind is like a little bit of an easier one to relate. Let me just get rid of all that extra stuff. And then similarly for I'm not going to go through it, but if you were to draw tangent lines on the concave down one, they're getting steeper, but because they're negative, they're decreasing. So I want to just, while we have these pictures here, just summarize what we can say about the first and second derivative for each of these. So this first graph is increasing and concave up. So what does that tell us about the derivatives? Well, it would tell us that the first derivative is positive, right? Because it's increasing. And then the fact that it's concave up tells us that the second derivative is also positive. So what about the second one? Well, so the second one is increasing. So the first derivative is positive, and then it's concave down. So that tells us that the second derivative is negative. This third example is decreasing, right? So that means the first derivative is negative, but it's concave up. So that means the second derivative is positive. And then this last one is decreasing. So the first derivative is negative, and it's also concave down. So the second derivative is also negative. So you can have really any, mix and match first and second derivative, and you can get a graph that has that feature. Okay, so the last thing I want to do is, or actually, sorry, not quite last, but I want to now look at the graph of the first function that we were talking about and talk about concavity as it relates to this function. So if we look at this graph, we can see that the graph starts off concave down, and it can be a little tricky to see on a graph exactly like where the graph changes and where it's concave down. In tomorrow's video, we'll get into some methods that let us know, like for absolutely sure, where are things concave up or down. But just looking at this graph, it looks to me, and I happen to know like that this is the actual answer, it looks to me that this part of the graph, so from here all the way to here, is concave down. Whereas this part of the graph is concave up. And then at 0, it's actually neither. And again, we'll get to that in tomorrow's video. So what could we say here? We could say the function f of x, and let me just write on here again, this was still the same function, x cubed minus 3x. So we can say that f of x is concave down on the interval from -∞ to 0, not including 0. And so that tells us that the second derivative is negative on that interval. And then looking at the right-hand part of the graph, we said that f of x is concave up on the interval from 0 to infinity. So everything from 0 on. And so that tells us that the second derivative is positive on that same interval. So let's look at the graph of the second derivative just to kind of confirm that it matches up. So the second derivative, so thinking back to, so here's our function, the first derivative was 3x squared minus 3. And so the second derivative is going to be 6x. So the second derivative is equal to 6x. And so just like we did for increasing and decreasing, we can see that things kind of line up the way that we'd expect. So the second derivative is negative on the first part of the graph, And so that corresponds to the fact that the, oops, I got mixed up with my colors. Let me change that to be consistent. So the first part of the graph is negative, right? It's below the x-axis. And so that corresponds to the fact that the graph was concave down. And then the right part of the graph from 0 onward, this is positive. It's above the x-axis, and that matches up with the fact that the original function was concave up. Okay, so last thing I want to do is just a couple of examples of kind of figuring out what's going on at a particular part of a graph. So first thing I want to do is looking at this function. So let's call this function f of x, and we don't have an equation for this. We're just going to say this is f of x. So what I want to do is basically try to figure out, so first thing is whether, so let me think of how I want to word this. So I want to determine the sign, S-I-G-N. So when I say that, I mean basically whether they're positive or negative of f of x, or sorry, I want to look at a specific number. So f of 1, f prime of 1, and f double prime of 1. So I basically want to figure out at x is equal to 1, is the function itself positive or negative, is the first derivative positive or negative, and is the second derivative positive or negative. So let's look at what's going on at x is equal to 1. So that is like right here. So first question is f of 1 positive or negative? So f of 1 is positive, right? Because it lies above the x-axis. So when we're talking about the function itself being positive or negative, that is not referring to increasing, decreasing, concave up, concave down. That's literally just asking, is the function above or below the x-axis? So f of 1 is positive because it lies above the x-axis. Okay, what about the first derivative? So f prime of 1. Well, on this part of the graph, the function's increasing, right? If you were to draw a tangent line here, it would have a positive slope. So that tells us that the first derivative at 1 is positive because the graph is increasing. Or I should just say, I'll just say because f of x is increasing at x is equal to 1. And then what can we say about the second derivative at 1? Well, this part of the graph is concave down, right? 1 lies on a part of the graph where it's like you're spilling your cup of water, right? It's upside down. So that tells us that the second derivative is negative, and that's because f of x is concave down. Not everywhere, but it's concave down at that point, right? I'll just go over here. Sorry, I'm not sure exactly where the border of my page cuts off, so hopefully you can see all of that. Let's do the same thing at x is equal to 3. So I would encourage you to try this one yourself. So we're going to determine the signs of f of 3, f prime of 3, and f double prime of 3. So I'd encourage you to pause the video and try this yourself. Try to figure out whether they're positive or negative. So here's the point on our graph. So first thing we can say is that f of 3 itself is negative, right? It's less than 0, and that's because it lies below the x-axis. Okay, what about the first derivative, so f prime of 3? Well, in this case, the function is decreasing. The slope of the tangent line would be negative. So that would tell us that the first derivative is negative. So because f of x is decreasing at that particular x value. And then the last thing is that portion of the graph is concave up, right? It looks like if you were to pour water on it, it would collect that water. So f double prime of 3 is positive, and that's because not everywhere, but at that part of the graph, f of x is concave up. Okay, I want to do one more example in this video. It's kind of a variant of like what we just did. So let's say now that I'm going to give you not the original function, but the derivative. So suppose that f prime of x is equal to x squared minus 5. So without figuring out what f of x is, we don't need to do that. We're going to answer these questions just based on the derivative. We want to figure out whether f of x is increasing or decreasing, and whether it's concave up or concave down at x is equal to 1. So at x is equal to 1 is f of x, so the original function, not not x squared minus 1, increasing or decreasing. And then also, is it concave up or concave down? Okay, so how can we answer the first part of this? Well, to figure out whether it's increasing or decreasing, we just want to see whether the derivative is positive or negative when x is equal to 1. So for this part, we can actually just plug in 1 because we already know what our derivative is, right? So we can plug in 1 and we can find that we get 1 minus 5, which is negative 4. And so because the first derivative was negative, that tells us that f of x is decreasing at x is equal to 1. So what about the second part? So in order to figure out whether it's concave up or concave down, we're going to want to figure out the second derivative. So because we already have the first derivative, we can just find the second derivative. So the second derivative is going to be just 2x. So now we can plug in 1 into that, and we get 2 times 1, which is 2. And that's a positive number. And so that tells us that f of x is concave up at x is equal to 1. So hopefully from these few examples, you can kind of see how, like in the first example, we were given the original function and we figured out stuff about the derivative, right? Like we looked at f of x, and from f of x, we figured out stuff about f prime of x and f double prime of x. And then the second example is the opposite. We were given the derivative and we use the derivative to figure out information about the original function. So it's really a two-way street in these types of questions. So like I said, tomorrow we'll get more into examples where we'll kind of from scratch figure out all of the different ways the function's increasing, decreasing, concave up, concave down. Yeah, so I will see you tomorrow.